So here's the lecture for section 7.2, areas in the plane. Um, Big idea here. We know that the Riemann sum allows us to add up essentially what feels like a bunch of areas, rectangles that fill up a space. Um, when we did that, we always sort of went from the curve down to the axis, but now we'd like to look at what happens when we're doing areas in the plane that aren't strictly bound by an x-axis. So if we think about a space being defined by an upper curve and a lower curve, and we think about filling those curves up with a bunch of rectangles, each of those rectangles, let's say, being delta x wide. Um, and maybe when we think about having an infinite number of rectangles, that delta x could be thought of as a dx. We think about the distance between the curves, the upper curve having a higher y value and the lower curve having a lower y value, that the difference between those two y values not only is the height of the rectangle, but as long as we always put the taller, higher curve first, that distance will always be positive. So to summarize, the area between the curves could be thought of as the integral of the upper curve minus the lower curve, and then multiply that expression by dx, the width of the individual rectangles as x varies from A to B. Let's do some sample problems using this idea. Almost always these problems we're going to need to draw out the space that we're talking about. So, for example, um, if we are talking about this area between the secant squared curve and the sine curve, well, I know that the secant curve starts at 1, secant squared will start the same, and kind of has an upward, uh, upward, not parabolic, but an upward slope there. The sine curve starts here and then makes its way. No, it doesn't go that high, it goes up to 1. And if we're talking about going from 0 to pi over 4, we're essentially talking about this space in here. Okay? We recognize that the upper curve is the secant square curve, that the lower curve is the sine curve, and we want to look at the area between those curves as x goes between 0 and pi over 4. If we take the antiderivative of secant squared, well, that's tangent. Antiderivative of sine is negative cosine. So that's going to net out to a plus cosine. And we're going to evaluate this expression as x goes from 0 to pi over 4. Um, let's see, that's going to be tangent of pi over 4 plus the cosine of pi over 4 minus tangent of 0 plus the cosine of 0. And let's see what we get there. Tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2 minus cosine or tangent of 0 is 0. Cosine of 0 is 1. If I distribute that through, I've got a positive 1, I got a negative 1. Those two cancel out. It looks like this region's area is root 2 over 2. All right. Um, let's do another one. Again, let's start with a drawing. This case, the parabola 2 minus x squared. I'm going to go up 2, and I'm going to go down. I'm going to take a look at the line y equal negative x. That goes like this. Oh, so it looks like these parabola and line cross in two places. Let's find that those intersection points. Um, I've got 2 minus x squared is equal to negative x. Take the x squared over to that side. Take the 2 over to the other side. Um, I think that factors. How about x minus 2 and x plus 1? Which means x minus 2 equals 0, or x equals 2 is one intersection point. It looks like there. And then x plus 1 equals 0 is in going to lead to an intersection point, and that's 1, that or -1. That looks like there, and that looks about right. So we'll write that integral. It's going to be as x goes from -1 to 2. The upper curve is that parabola. The lower curve is that line. And so we'll clean that up a little bit. Integral from 1 to 2 of, I guess that'd be -x squared plus x plus 2 dx. All right, let's get ready to find the antiderivative there. Antiderivative of -x squared is going to be -1/3 x cubed, and then plus 1/2 x squared, and then antiderivative of 2 is 2x. We're going to do this as x goes again from -1 to 2. So evaluating at the high end, I am going to get -1/3 2 cubed plus 1/2 2 squared plus 2 times 2 is my high end. And at my low end, plug in 1, I'm going to get -1/3 and positive 1/2 and positive 2. Oops, sorry, I got that wrong. Let me try that again. -1 to the 1 to the third is -1, so it's a positive 1/3. -1 squared, that's just going to remain positive, and -1 times -2 should be give me a -2 there. Okay, let's see if we can clean that up. How about -8/3 plus 2 plus 4? Good there. Minus the quantity. And now here I'm probably, let's find a common denominator. How about 6? How about 2/6 plus 3/6 minus 12/6? -8/3 plus 6 minus, and that's -12 plus 5, -7, -7/6. Super plus that. Let's go. I need common denominator one more time, this time 6. So how about -24/6 plus 36/6 plus 7/6? Um, that'd be uh, that would be 36 plus 7 is 43. 43 minus 24 um, appears to be not right. Let me see where I screwed up. 36/6. Oh, here's my problem. 8/3, I have to multiply top and bottom by 2. This is -16/6. That's where I'm going wrong. All right, so I've got 43 minus 16, 3, 13 minus 6 is 7, and then 27. So I've got 27/6, which is equal to 9/2. Whew, got there in the end. All righty, let's do another one. Find the area enclosed by the parabola. That's not a parabola. By the curve y equal to cosine x, and the line y equals, well, this is not a line, this is a parabola. Oh, gonna have to edit that. Okay, so let's draw it out. 2 cosine starts up here at 2, and kind of goes down by the time we get to pi, and as we get to negative pi, x squared minus 1. Start here at -1, and we kind of go up. So these two curves are going to have intersections. And if I try to do what I did last time, that is setting 2 cosine x equal to x squared minus 1, we're going to realize that we don't have good analytical tools to be able to solve that equation. And this is just one of the places where we're going to definitely need to go to the calculator uh, to get this worked out. So let's switch over to the calculator. Let's start a new document. Let's go into graphing mode, and our graph. Um, do I need graphing mode? Yeah, I need graphing mode. Um, I've got uh, I've got two cos two cosine of x. There's one curve, just like I expected, and then let's add the second curve, x squared minus 1. There's our second curve, and now we want to find out where that intersection is. So I'm going to go into Menu, Analyze the Graph. I'm looking for intersection. That's option number 4. My lower bound be here, my upper bound here, and there I have it, 1.27. Now, the College Board asks that we actually find that intermediate answer to 6 decimal places. So I'm gonna hover my cursor above the 1.27 and repeatedly hit the plus button until I get all the decimal places I need. It looks like it's 1.26, 1.26 7 or 5424. All right, so let me put that down. I'm going to mark here that I'm going to just call this A. And by the way, because of symmetry, this is negative A. And I'm going to declare A to be that 1.265424. Right? And now I can say, oh, this area is going to be the integral from negative A to A of the 2 cosine x on top and minus the parabola x squared minus 1 on the bottom dx. All right. Since we're already in calculator mode, why don't we use the calculator to find the value of that integral? To do that, what I think I'd like to do is I'm going to take this number that marked the x value of the intersection. I'm going to click it. I'm going to store it. And I'm going to call it A, just like I did on the paper. And now when I open a calculator page, any reference to the variable A has that value in it. Even though it's only showing 5 decimal places, there's more decimal places being stored internally. Let's go ahead. Let's do the integral from negative A, never having to type that in again, or even once, to positive A. And geez, I think I have those two functions actually listed in my grapher. The cosine one was called f1, f1 of x. And let's subtract it by the other one, which we called f2. Again, no need to type it in. Always a possibility of making a mistake if we did that. Oh, forgot to put the x in. Enter. And got 4.99. We'd write that down on our paper as 4.995. It's a final answer. 4.995. By the way, because of the symmetry, we might have also written our expression as 2 times 0 to A of 2 cosine of x minus x squared minus 1. And if we did that, we should, out of the calculator, get the same answer. Let's go ahead and put a 2 in front. change that lower bound of integration to 0, and we do get the same answer. All right, looking good. All right. Back to the notes. The gotta be careful. Not every boundary, not every curve that we could draw has nice curve to curve changes. For example, let R be in the first quadrant bounded by y equal x squared or square root of x, which looks kind of like this. And below by the x-axis and the line y equal x minus 2. If I go down 2, it goes up here, crosses there. And so the boundary, draw this in, the boundary of the region that we're talking about kind of looks like that, right? Not strictly speaking, there's not a lower curve all the way through. We might want to do a couple of different things to make this work. We might, if we want that red region, we could find the area of, let's say, this green region, and then subtract out that triangle and get something like the integral from, well, first of all, we're going to need to know what that intersection is. Okay, intersection, let's calculate that. When does x, when does the square root of x equal to x minus 2? Square both sides, I get x is equal to what? X squared minus 4x plus 4. And let's subtract x from both sides. I get 0 is equal to x squared minus 5x plus 4. And I think that factors as x minus 4 and x minus 1. And that looks confusing until you realize that this is 4 and this x minus 1 is the value you would have gotten had you extended that half parabola down below the curve. All right, so now we know that the green region can be thought of as the integral from 0 to 4 of the square root of x. And then maybe we subtract out, again, that triangle, which is 1/2 the height. Let's see, this is probably 4, 2, this width. I think this goes to the point 2, 0, because 2, 0 is on that line. So that triangle is 1/2 2 by 2. So let's put all the pieces together. Definite integral of x to the 1/2 dx minus 2. Make the exponent 1 bigger, multiply by the reciprocal of that exponent, and evaluate this from 0 to 4, and the result will subtract by 2. Let's see, 2/3, 4 to the 3/2, minus 2/3, 0 to the 3/2. And then this whole thing is subtracted by 2. 4 to the 3/2, take the square root of 4, you get 2, cube the 2, you get 8, times that by 2, you get 16/3 minus 2, 16/3 minus 6/3, which ends up being 10/3. And I believe that is the answer. Again, not the only way that we could do that problem. We might have also broken this up into 2 integrals. Maybe go from 0 to 2 and only do the square root part. But from 2 to 4, we do the square root part minus the line. And theoretically, that integral should give us the same answer as well. Multiple ways to do this. All right. every single problem that I've been doing in call it the DX orientation, making skinny rectangles that are DX wide. Um, but it ends up that we can also make the skinny rectangles DY tall and make them squat, um, depending on the shape of the region that we're working with. It actually may be advantageous to draw it and use this orientation. In fact, let's do the problem that we just did, where again we had our axes, we had the square root function, and we had that line. Okay. But now let's see, I can make my rectangles in the dy orientation, each of these rectangles dy tall. And now the width of the rectangles are the x value to the right, which will give us the largest x value, minus the x value to the left, which gives us the smaller x value. So we might say that is the integral of the x value to the right. It was originally written as y is equal to x minus 2, but if I solve for x, I can see that the taller curve now, the one further to the right, is the y plus 2 curve. If I do the same, what is the curve further to the left? That'd be y squared is equal to x. So y squared dy. And we want to go from the lowest y, which was 0, to the highest y. And remember, we determined that this was the point 4, 2. So the highest y is 2. So some 0 to 2. And we can see that this expression does seem a lot simpler than the one that we worked with earlier. Let's go ahead and take that antiderivative. 1/2 y squared plus 2y minus 1/3 y cubed as evaluated from 0 to 2. So I get 1/2 2 squared plus 2 times 2 minus 1/3 2 cubed. That's me evaluating at the high end. At the low end, I get 0 plus 0 minus 0. Can ignore a bunch of that. 1/2 of 4 is 2 plus 2, sorry, plus 4, and then minus 8 thirds. So 6 minus 8 thirds, common denominator of 3. How about 18 thirds minus 8 thirds is equal to 10 thirds? And of course, we're happy to see that because that's exactly the same answer that we got when we did it in the dx orientation. It's my belief that the dy orientation in this problem was a little easier.